Okay, first things first. Click and close, have a quick look. So I added, and I meant for this assignment to be up Friday, forgot to push the button, or pushed the button and something didn't work. I don't remember which happened, but either way, it wasn't there. So it is available now. It's the 1.2 practice 3. So there's 3 parts to the 2.1, sorry. 2.1 has 3 parts. The third part deals with some of the stuff that we talked about last Friday. Okay, so evaluating functions. Just keep in mind when you see crazy stuff like this, where you're inputting variables into functions instead of just inputting numbers, keep in mind that you're following the same patterns and rules that you do with numbers, right? When we evaluate a function, let's get phones away, please. When we evaluate a function, what do? The function tells us what the rule is for treating inputs. For example, in f of x is negative 4x plus 9. So when I input an x, I'm multiplying by negative 4 and adding 9. That's the rule I'm going to follow with any input, right? It's defined for x's right now, but it could be anything. So if I were to input an a, well, then I would just multiply it by negative 4 and add 9. And I'm stuck with that, negative 4a plus 9. I've got a variable in my answer. If I input a 2, negative 4 times 2 plus 9, I can simplify all of that because they're numbers. They're like terms, right? I'd get negative 8 plus 9 is 1. What if I input something like c plus 2? Well, I'm going to do the same pattern to it. I'm going to multiply the quantity c plus 2 times negative 4 and then add 9, right? People are sometimes wanting to do too much to this stuff. They're wanting to do more than they're supposed to do. When you're evaluating a function, the answer is whatever the function outputs. Sometimes I saw people trying to do things like they'd get this answer and then they wanted to subtract the 1 to isolate the c or something goofy like that. That's not what we do. This is the answer. When I input c plus 2, this is what the output is. I just need to simplify it a little bit, though. That is the answer. It's just not simplified. It'd be like saying your answer is 6/4 instead of simplifying it to 3/2, right? This is the correct answer, but when we simplify it, we can write it like that. Make sense? Okay, so, we did an example like with g of x. G of x is x squared minus 5. So now when we input something, we're going to square it and then subtract 5. If I input a minus 3, well then I'm going to square the quantity a minus 3 and then subtract 5. There's a little more work to do to simplify this one though, right? I've got to FOIL that out. A minus 3 squared, I've got to take a minus 3 times a minus 3, FOIL everything out, add like terms, and eventually get my simplified answer. Okay? What if we have an expression involving multiple functions like this? G of 2m plus 1 minus f of 3m minus 7. That's all right. We're just going to figure out what the output is for g when I input 2m plus 1. That's one little mini problem all on its own. So we input 2m plus 1 into g, and what did we get when we did that? Oh, okay, I didn't go through the steps. But if I did, I'd have to square out 2m plus 1, quantity squared, minus 5. So I have to FOIL all that stuff out and then subtract 5. And if I did that, same kind of thing I did in problem 19, when I did all that work, this is what the simplified output would be for the blue part. Okay? What if I input 3m minus 7 into f? So I'd have negative 4 times the quantity, 3m minus 7, and then add 9 at the end. If I simplified that whole thing, did all the work, the output, the red output, would just be that stuff right there. Okay? What am I going to do with those? Well, it looks like we want the blue output minus the red output, right? So I've got the blue stuff minus the red stuff in brackets or parentheses, because I have to subtract the whole thing. Bailey, yep. You put the into which one where are you looking up here? Oh, right. I see. Right, exactly. So you're wondering, how did I get this stuff? Okay, let's go through how we got this stuff. I didn't show the steps, but how would we get there? Here are the invisible steps. So f of, I'm just going to put a box. We'll just kind of box this area off. So f of 3m minus 7 would equal negative 4 times the quantity 3m minus 7 plus 9. Right? So I've got to distribute the negative 4. So negative 4 times 3m is negative 12m. Negative 4 times negative 7 is plus 28 plus 9. There you go. Okay. Does that make sense? Okay. This one was a little tougher. This one right here, we would have had to do this. G of 2m plus 1 would have been, there's g of x, right? So g of 2m plus 1, what does my function tell me to do with the input? First thing I'm going to do is square it. So I've got the quantity 2m plus 1 squared minus 5, right? So then I would have to square that out, I have to multiply it by itself in FOIL. That's all right. So then, you see what I'm saying? So then, if I did all that stuff, if I distributed the 2m, okay, what's that going to give me? 4m squared, right, plus 2m. If I distributed the 1, whoops, I'm going to get plus 2m plus 1, and then at the end I've got my minus 5. And if I add all that stuff up, that's going to give me 4m squared plus 4m minus 4. Okay, see where I'm going with that? Okay? All right, so you're going to have some problems like that in the last assigned problem set. Okay? There's some problems at the end of 2.1 practice 2. These are not hard, but I want to explain it to you. They're not hard at all, but we need to maybe talk about it for just a second. So determine the largest open intervals of the domain. So that's important, of the domain. So we're talking about values of x or y. X, right? Domain is x. So we want the values of x where the function is increasing, first of all, and then decreasing. So let's do increasing first. What do you suppose it means for a function to be increasing? Okay, so going up, but going up from where to where? Let's just click that a little closer. You're fine. So, okay, but as the ant is moving in the x direction, yes, sir? Has a positive slope, yeah, so, right. So when the ant is walking in the positive x direction, the function, meaning the y values, are getting bigger when the ant is walking uphill, meaning it has a positive slope. So we're just trying to find all the places on this graph where that's true, where an ant walking from left to right is walking uphill. So what's one interval where that is happening? Say it again. Where he's walking up. Yep. Okay, there's one right there. Everybody see that? Okay, Carter, he tells us negative infinity to negative 5. That's correct, right? Because wouldn't you agree that all this arrow means that this graph goes forever, right? The ant walking from negative infinity would be walking uphill the entire time until he gets up to negative 5. Finally, his long journey is over, and he's not walking uphill anymore. He gets to the crest of that peak, right? Yes. Okay, excellent question. That's my next question to you, in fact. Would we include negative 5? Is the function increasing at negative 5? No, it's not, because that's a point of transition, isn't it? Yes, sir. Well, you can see why they did here, because it's kind of a weird. I mean, the reason they gave it to you is so you could see what the x value was. Yeah, and typically, yes, you will. Yeah. Okay, so then that interval right there, that part would be. Agreed? Okay, we can see that if we project that part of the graph onto the x-axis, we'd get an endpoint down there at negative 5, and it would just go to the left, wouldn't it? Everybody agree? Okay. Where's another interval where the ant would be walking uphill? Right, and we're only interested in the x values here. 5 till when? Infinity. There you go. Yeah, so here's the other one. Right there. Okay, so that one's going to be 5 to infinity. Okay, now how do I say or? With a U. Okay, now sometimes, and I think on the assignment it actually asks you to do this, sometimes they're going to tell you to use a comma, because that's another way to say or. You can either say a U or you can say a comma. Like in calculus, a lot of times, we'll just put a comma there. That's because we get lazy, I guess. But comma can also mean or. Okay? So be careful to read the instructions and see which one it's wanting you to put. Yeah. Yeah. So just make sure you read the instructions. If it's telling you to input a comma between answers or between intervals, then use a comma instead. If I project this one up, it just looks like that. And look what we've got then. We've got this or statement, don't we? Right? How would I say that using inequalities instead of intervals? X is what? Less than negative 5, or, remember, or is the V with inequalities. What about it? Greater than 5. There you go. Perfect. Okay, good. Now, what about part B? Oh, we'll find out. Decreasing. So part B, where is this function decreasing? That must be where the ant's walking downhill. From where to where? Negative 5 to 5. Because remember, I'm looking at x values. The most common mistake, and I guarantee when you're, almost everybody's going to make this mistake at least once, because you're focusing on other things. And when you say increasing or decreasing, you're thinking vertically, aren't you? So people are, what you're going to tend to do is you're going to look at this, you're going to say, okay, y values, vertical values. And you're going to say 25 to negative 25. But we're looking for the x values where this is happening. So it's going to be on the interval from negative 5 to 5. And again, we're not including the endpoints, right? In the same way that 0 is neither negative nor positive, it's the transition between the two, right? It's the boundary. This point right here is the boundary between increasing and decreasing, and this is the boundary between decreasing and increasing. But at the point, you're doing neither one of those things. Make sense? Okay? How would I say that with x's? Then negative 5 and less than 5. There you go, right? Okay, and then the last part, where is it constant? Okay, now what would a constant function look like? Horizontal. Are there any places on this graph where it's horizontal? No, there are not. And you can't say at those points, because a point is not enough. Remember, a point by itself, how can that really be horizontal? The function is not horizontal there because it's transitioning from increasing to decreasing, right? So in calculus, we'd say that the tangent to the curve is horizontal, but the function or the curve itself is not horizontal. So there are no places where it's constant. It would have to have some interval where the ant could take at least one infinitesimally small step and travel horizontally. He could never do that here. No matter how small a step he takes from that point, he's going downhill, right? no matter how small a step he takes to get to that point, he's going uphill. See my point? Okay? Exactly. Yeah, exactly. It would do something like this, where it would go like that. Okay? And there would be constant. Okay, make sense? Okay, good. All right, let's figure out who the big winner is here.